So, welcome to this new lecture. Now, here last time what we did was we finished our discussion on module 4, in which we discussed frequency dependence of dielectric constant, and we found that dielectric constant has various regimes, and first high frequency regimes are two regimes. One is this electronic polarization and second is ionic polarization, and in those two regions you see presence of this resonance, and this resonance is characterized by a characteristic resonance frequency, and above this frequency the particular mechanism ceases to operate, because the field is switching faster than the dipoles can respond, than the speed at which dipoles can respond to. And then we looked at the low frequency region, which corresponds to the dipolar polarization or orientation polarization, and in that case the mechanism changes from resonance to relaxation, because there it's about movement of molecules or group of molecules from one position to another, and that requires that is a diffusive process. As a result, you have a characteristic relaxation time, and from that we got what is called as a relaxation equation, and solution of that relaxation equation gives rise to what we call as Debye equations. So, Debye so when we then plot this dielectric constant versus frequency, you get a complete understanding of the picture that emerges as a result of frequency dependence. And then finally, we looked at impedance spectroscopy, which was essentially a way to model these dielectric materials, because the response of these dielectric materials in reality is never ideal. So, as a result, you have various deviations from ideality that could be because of presence of a variety of defects such as grain boundaries, such as electrode material interfaces, and all of these they give various contributions. And impedance spectroscopy, as we looked at, was basically if you have perfect dielectric, it should give you one half circle, and if you have more than one or two contributions coming from various other mechanisms, then you will get multiple circles, and many times these circles overlap with each other, half circles overlap with each other, and it's very essential in that case to understand what is happening there. And it's not an easy affair, it's a complicated affair, but by proper modeling and proper designing an electrical equivalent circuit, you can come out with some good answers. And then finally, we looked at what we called as breakdown mechanisms. So, dielectrics do break down, as you must have often seen that the electric poles on the streets have dielectric capacitors, and often there is a sparking there, and that sparking is a sign of their breakdown. And there are breakdowns with intrinsic mechanism, and then secondary mechanisms, or primary or secondary mechanisms, and all of these mechanisms lead to dielectric failure, which means the dielectric no longer remains a dielectric, it becomes conducting, or it becomes useless as a dielectric. So, the dielectrics that we discussed were essentially linear dielectrics. So, module 4 was about linear dielectrics, and what essentially it means is that when you in these linear dielectrics, the dependence of polarization on electric field is linear, because we looked at this P was equal to epsilon naught epsilon r minus 1 into E. So, there was this overall this linear dependence upon the field. So, when you plot polarization versus electric field, the plot must be linear, it is a linear plot. Okay. Now, there are some dielectrics other than these dielectrics which are non-linear. So, these non-linear dielectrics have a curve which is not like this, rather you might have a curve something like this. Okay. Now, here there is no linearity associated as compared to previous. So, this is your linear dielectric, and this is what is called as non-linear dielectric. And there are a variety of classes of these nonlinear dielectrics, and that is what we are going to look at in this lecture by considering variety of these dielectrics and how they work, what are their different characteristics, etc. So, now these nonlinear dielectrics are very special dielectrics because they have very special characteristics, and some of those characteristics could be, so if we just some of these characteristics, for instance, could be very large dielectric constants, this is only one feature, there are many other features. For instance, they show some very very special effects, and these effects could be, for instance, interdependence of or coupling of strain or mechanical and electrical order parameters. So, you can say coupling of, let us say, a stress or a strain with electrical parameters and this is referred as piezoelectric ceramics. The materials which show this kind of behavior are called as piezoelectrics. Now, the word piezoelectric itself means, piezo means piezo or piezo, it means stress or force, and it is a Greek word, and then electrics, of course, you know that it means by electrical force. So, coupling of electrical and mechanical order parameters, which can be taken as order parameter in case of electrical order parameter in dielectrics can be taken as polarization, and in case of mechanical order parameter it could be strain. So, coupling of strain and polarization is called as piezoelectric effect, and these are very useful effects because they give rise to variety of applications. So, when you have this, for instance, a material so piezoelectrics, what happens is in piezoelectric is when you apply so electric field application gives rise to what is called as strain, and conversely if you apply stress to the material it shows polarization. So, there is a coupling between these two order parameters, and this effect is extremely useful because if when you apply for instance when you apply electric field and you get strain out of it, what can it be? You can use it for variety of applications. You can, for instance, make a transducer or an actuator. So, by changing the electric field slightly, you for instance, you make an opening in a pump, and the size of this opening can be changed by changing the magnitude of electric field, because electric field will induce a strain which will allow this opening to collapse or expand. Similarly, when you apply stress, then you can measure the charges that are created on the surface of this material, and this is nothing but your piezoelectric converse piezoelectric effect, and this can be again used for variety of applications. So, these materials are used for sensors, variety of sensors, strain sensors, for example. You can use them for actuators. They are used for transducers, etc., etc., and we look at some of these applications when we discuss these materials in detail. So, this is one effect that is not seen in normal dielectric or linear dielectrics. So, that is why it is a special effect, and this effect is nonlinear in nature, it is not linear. Second, you can have a temperature dependence of polarization. So, in this temperature effect, what will happen is, if you have a dielectric material and you subject this dielectric material to change in temperature, then you have some charge which is introduced on the surface. So, this is basically temperature induced changes. So, this is such kind of materials are called as pyroelectrics. Now, here again you can see this word pyro means high temperature, and electrics means, of course, something to do with electricity or electrical parameters. So, coupling of these two, temperature and electric parameters, gives rise to this pyroelectric effect, and this is again a very useful effect because it is used in variety of applications such as your alarms. It's used in IR imaging, etc. And we will again look at this effect in detail. And the third effect, which is a very special effect again, is presence of large polarization. Large polarization, which is with a hysteresis behavior. So, when you switch material, it shows this kind of behavior. So, this is a polarization electric field. So, what it has a two non-zero states of polarization. So, minus PR and plus PR. PR is remnant polarization, and these two states are available at zero field, and this effect is called as ferroelectric, and materials which show this effect are called as ferroelectrics. So, ferroelectrics is a very special class of materials, and again, when you see this kind of, so what you have here is two non-zero states of charge at zero field, which means this can be used as a material for binary data storage. So, this can be used as a 0, this can be used as a 1. So, 0 1 is binary data storage. So, this material can be used in the form of memories which are non-volatile in nature, and this is very important because in contrast to this is a very important application, because in contrast to magnetic memories, as you know that most of the memories currently are magnetic in nature. The problem with magnetic memories is that their speed of operation is slow. In contrast, speed of operation of ferroelectrics, for some reasons which we will see later, is very fast. So, as a result, this material is extremely fast in nature, but at the same time it is non-volatile. The reason why magnetic memory is used, because it is non-volatile in nature. When you take the power off, it still stores the data. However, in order to run this computer beautifully in a fast manner, you have to use a buffer memory, and this buffer memory is called as DRAM. It is called as dynamic random access memory. So, if you can make this ferroelectric work as a memory, you can get rid of DRAM and magnetic memory altogether. So, you will just work on this one hard disk, which will be operating extremely fast. So, this is one of the very well perceived application of very well thought out applications of ferroelectrics. And there have been challenges in making those memories, so that is a fabrication problem, but characteristic wise or as a principle, this is a very neat principle. So, again, so these typically these three effects, piezoelectric effect, pyroelectric effect and ferroelectric effect, put together they make these materials extremely interesting for a variety of commercial applications, and that is why they are extremely fascinating to study, and they have been studied for a long time. And what we will do in this module is that we will look at characteristics of individually each of these materials separately. However, before we do that, we have to establish a basis on which we can define these materials in a different class. So, what we will do is that we will first establish a crystallographic basis which separates these materials from other materials, and then we will individually go into that. So, these materials. So, now what makes these materials stand out as compared to other materials? The basis for this is the crystallographic basis. So, crystallographic classification, let us say. Now, these materials are different because crystallographically they also happen to be rather different from other materials. Now, before we do that, we have to understand. Now, we know there are seven crystal systems, as we have learnt in module 1. Then you have 14 Bravais lattices, and on top of that you have variety of symmetry operations that we talked about in the first module. And as we know that these symmetry operations were rotation, you had a mirror plane, and then you had inversion, and then you had rotation inversion or roto inversion. So, what rotation was, I will just briefly go through that. Rotation is essentially, so suppose you take a cube, or you take this square in 2D. So, for instance, I rotate this material perpendicular to the face of. So, this is this circle and the dot represent the axis which is going perpendicular to the face of this square. So, what is the symmetry operation? So, this is position number 1. Okay. Now, what is the symmetry operation that you need to perform? So, this is let us say square. So, in order to bring this square back into the same position, which means 1 should look like 1, you need to perform a rotation. So, let us say I do rotation operation here. So, when I do rotation operation here, if I do by pi by 2, then I basically, if this is 1, 2, 3, 4, if I do pi by 2, let us say anti-clockwise, then I take 1 here and 3 here, but since it is a square, which means it looks same. So, this pi by 2 is a rotation operation which allows this crystal to, or this face to come back in the original position. Now, the question is, what is the minimum angle by which you can rotate it to, and that minimum angle is pi by 4. So, if you do it by pi by 4, 90 degrees. So, which means 1 goes here, 2 goes here, 3 goes here, 4 goes here, and still it looks the same. So, this pi by 4 is essentially sorry, hang on, this should have been pi, and this should be pi by 2. So, this is 180 degrees, this is 90 degrees. So, please make that, note that this was pi and this was pi by 2. So, if you now rotate this by 90 degrees, it again comes back to the original situation, and this is called as 4-fold rotation. So, as we looked earlier, the rotation axis is defined as n-fold would mean n-fold would mean 360 degrees divided by theta, and that theta could be pi by 2, it could be pi by 3, it could be pi by 6, it could be pi or 2 pi, or alternatively this angle theta would be 360 degrees divided by n. Okay. So, this n-fold symmetry, for instance, a 4-fold symmetry for a material would mean that you need to rotate that material or that crystal along around a particular axis by that much angle, which is sufficient to bring that material back into the original position. Similarly, you had this what we called as mirror plane. So, again if you draw this cube, this face here, and if I draw this plane here, this is the mirror plane, because anything on the left of this plane looks exactly similar to this right plane. Similarly, you have a mirror plane here. It's not a very good drawing by me. So, again this is a mirror plane. So, these are the variety of mirror planes that you can have. So, mirror plane is again an operation which makes a crystal exactly look similar on the both sides of the mirror planes. And then you have inversion. So, inversion would be bring this point from 1 to let us say 1 prime, or take basically from let us say if you take in 3D, then take plus x plus y plus z to minus x minus y and minus z. So, this is your inversion. And the fourth operation that we looked in module 1 was called as rotation inversion. So, you rotate and then invert. Now, combination of these geometric symmetry operations gives rise to what is called as point groups. So, point groups are combination of these symmetry operations. And based on these 7 crystal systems, for these 7 crystal systems you have 32 point groups. Now, point groups are of course denoted in various different ways. One of the ways to differentiate point group is you can use full symmetry symbol. So, for instance, this full symmetry symbol, and this notation is often called as your Hermann Maguin notation, which is basically a method to represent the symmetry elements in the point groups, and it is basically a notation named after this German scientist Hermann and French scientist Maguin. So, this is often it is called as the international notation as well. So, this is a very convenient way of representing the symmetry. So, for instance, so rotation symmetry is given as 360 degree divided by n or 2 pi by n, where n is the rotation symmetry. Then you have m, which represents mirror plane. So, for instance, if you have for a given material, let us say a cubic material, you have 4 by 1 is the symmetry element for a material, which means the material only has a one-fold symmetry, which is nothing but 2 pi. So, which means this material is the worst possible candidate in terms of symmetry operations. And then for instance, you can also have 2 to 2, and this 2 to 2 will mean this material has 3 two-fold axis. And for instance, if you have something like 6 to 2, so this has 1 6-fold and 2 two-fold axis symmetry. If you have symmetry like written as 4 by m, what it means is that it has a 4-fold rotation symmetry combined with and a mirror perpendicular to rotation axis. So, likewise there are if you take for 7 crystal systems, so 7 crystal systems, there are 32 point groups, and you know what these 7 crystal systems are. So, these 7 crystal systems happen to be, so if you go to, so the first is cubic, and for cubic the symmetry elements happen to be the point groups happen to be M3 and M3 M, and then 432 bar 3 M and 2 3. So, M3 would mean it has a mirror axis and a 3-fold rotation, then it has mirror plane, then 3-fold symmetry, rotation symmetry, the another mirror plane. Similarly, a 4-fold rotation, 3-fold rotation and 2-fold rotation, and this would mean a 3-fold roto inversion followed by a mirror plane, and then this 2-3 will mean a 2-fold rotation axis and 3 would mean a 3-fold rotation axis. So, cubic has these symmetry elements. Likewise, tetragonal, orthorhombic, and then you have what is called as hexagonal, and then trigonal. Trigonal is nothing but rhombohedral, and then monoclinic, and then triclinic. So, there are 7 triclinic. So, there are 7 crystal systems. For all these 7 crystals, there are well defined notations. So, for instance, now I will go through. For cubic you had M3, M3M, 432, bar 3M and 2-3. For tetragonal we will have 4 or M. So, basically a 4-fold symmetry or M, which is equivalent mirror plane, or you will have 4 or MMM. So, either M or MMM, and then you will have 4 MM, bar 4, 2M and 2. Okay. So, these are symmetry elements for tetragonal. For orthorhombic we will have only 3, MMM or MM2 or 2. For hexagonal we have only 6 or M, which is similar, or 6 or MMM. Now, the 6 will mean 6-fold rotation, and then 6 and then 6 MM. Now, you must be wondering why I have these 6s differently. I will explain to that in a minute, to you in a minute. And then you have bar 6 and bar 6 M2 and then 6 to 2 and then so on and so forth. So, these again will have some symmetry elements. So, or maybe let me just write them. And then trigonal you have bar 3, bar 3M, 3, 3M and 3, 2. For monoclinic you have bar 1, 2 or M, 2 and then again M, and then for triclinic you have either bar 1 or 1, only 2 symmetry element. So, here you have 2 M or 2. Okay. Now, further these symmetry elements for each crystal system can be defined on the basis of whether the material is centrosymmetric or noncentrosymmetric. So, the question is, what is noncentrosymmetric or centrosymmetric? So, non-centrosymmetric. Centrosymmetric means a crystal which has a center of symmetry. So, centrosymmetric means a crystal having a center of symmetry. And geometrically what it would mean is that you have a center. For instance, you draw this cube here, right. So, in this cube, let us say I draw this boundary diagonal, and this is, let us say, a point O. Around this point I have symmetry operations. Center of this point O is center of symmetry, because anything that you see here at this position, let us say 1, is equivalent to what you see as 1 prime. So, this O becomes center of symmetry. In a more general fashion, what it means is that whatever you see at plus x, plus y and plus z is equivalent to minus x, minus y and minus z. So, a center of symmetry would be between these two positions, and on that particular center of symmetry, if you look either at plus x, plus y, plus z, or if you look at minus x, minus y, minus z across that center of symmetry, you would find the environment to be similar, which means that crystal has a center of symmetry. Non-centrosymmetric material would mean a material which does not have a center of symmetry, which means a crystal not having a center of symmetry. Okay. So, this not will come here, which means this plus x plus y plus z environment would not be equivalent to minus x minus y minus z across that center of across that point, which means that material does not have center of symmetry. So, based on this you can classify these crystals in two groups. So, one would be centrosymmetric crystals and other would be non-centrosymmetric crystals. So, now what I am going to do is that I am going to further classify these crystals. So, if I make here a table, so this is a crystal class, and then centrosymmetric point, and then non-centrosymmetric. Point groups. Now, even in the non-centrosymmetric, all the centrosymmetric point groups by definition are polar. Okay. So, non-polar, which means they do not have, if you take the average dipole moment or average polarization, because of symmetry, centrosymmetricity, there is no component which survives. In the non-centrosymmetric point groups, again you have two different groups. So, here I can divide this in two parts. One would be polar and one would be non-polar. So, some materials, despite being non-centrosymmetric, happen to be non-polar, and this would start from, for instance, let us say we start with cubic. So, if you take for cubic systems, for cubic system the centrosymmetric point groups are M3 and M3M, and for this polar it is none. There is nothing in cubic class which is polar and non-centrosymmetric. However, there are few which are non-polar, 432, bar 3M and 2,3. This is for cubic, and if you go for tetragonal, tetragonal would mean you have either 4 or M and 4 or MMM. So, you can say M and MMM, and then you have in polar you have 4 and then 4. So, I am just rewriting what I wrote earlier in the previous slide, but it is just that now I am differentiating these on the basis of centrosymmetric and non-centrosymmetric point groups, and further on the basis of whether the material is polar or non-polar. So, this becomes bar 4, 2M and then 2. So, just keep counting them, and then again I will not write the title header. So, here I will take now orthorhombic. So, in case of orthorhombic, your centrosymmetric point groups are MMM, and non-centrosymmetric point groups. So, if I just draw this line differently, so that this class you associate with non-centrosymmetric. So, this would be MM2 here only, and then 2. So, now it is trigonal. In case of trigonal, oh no, it should be hexagonal. In case of hexagonal, it will be 6 or M, 6 or MMM, and here it would be 6 MM, and it would be bar 6 M2 and 6 to 2. And now we will take rhombohedral. So, you have bar 3 and bar 3M, and here it would be 3M, and non-centrosymmetric non-polar would be 3,2. And then of course monoclinic. here it becomes 2 or m, and this would be 2 comma m, none. And then finally triclinic, bar 1, 1, none. So, if you now count, so what you get is total number of point groups, total is 32, centrosymmetric out of these, centrosymmetric are 11, and then non-centrosymmetric out of these are 31, well, or hang on, 21, and out of these 21, your 10 are polar and 11 are non-polar. Now, we have established a basis of crystallographic point groups and divided them into various groups. So, what we have is 11 centrosymmetric point groups for all crystal systems put together, 21 non-centrosymmetric point groups, and out of these 21 non-centrosymmetric you have 10 polar and 11 non-polar. Now, these three classes of materials, piezoelectric, pyroelectric and ferroelectrics, they first of all the materials which represent these effects, they have to be non-centrosymmetric, which means 21. So, non-centrosymmetricity is a must. Is a must condition, is a mandatory condition. Okay. So, these materials have to be non-centrosymmetric. Now, all the non-centrosymmetric point groups, which means 21 non-centrosymmetric point groups, out of these 21 non-centrosymmetric point groups except 432. So, this would be 20 point groups, and all these are non-centrosymmetric point groups. All the materials which belong to these 20 non-centrosymmetric point groups, whether polar or non-polar, they are all piezoelectric. So, essentially now the definition of a piezoelectric material would be, piezoelectric materials are those class of materials which are non-centrosymmetric in nature. They could be polar or non-polar except 432. Okay. 432 is an exception to this for the reasons simply because it happens in the non-polar category, and for some fundamental reasons it does not give rise to piezoelectricity. So, 20 non-centrosymmetric point groups happen to be piezoelectric. Now, so a piezoelectric material, as I said earlier also, 20 non-centrosymmetric point groups, the only exception is 432 point group, that is why it is 20. Now, out of these 20, out of 20 non-centrosymmetric point groups, you have 10 which are polar, and all of these 10 polar non-centrosymmetric point groups represent those materials which are called as pyroelectric. So, by definition you can see that all the pyroelectric materials are piezoelectric materials, but only those piezoelectric materials are pyroelectric which are non-centrosymmetric and polar. So, which means only 10 classes, and out of these 10 polar there are a few which are ferroelectric. Now, another definition of this pyroelectric material is, so non-centrosymmetric. So, one is non-centrosymmetricity, polar, which gives rise to only 10 point groups, and then they have a unique polar axis. The fact that material is polar, which means they have this unique polar axis, and along which which shows, so basically if you have a material like this, if this is the polar axis, which means the properties at the end, two ends of this axis will be different. So which means this is a unique polar axis. So these are the requirements for pyroelectric materials. Third is called as a ferroelectric, which is you have to now impose certain more constraint on the piezoelectric materials. So ferroelectrics would be polar, noncentrosymmetric, and unique polar axis, and the polarization along this polar axis must be reversible. So which means the polarization along polar axis must be reversible when direction of applied field is reversed. So basically what it means is that if you have a pyroelectric material, okay, let us say now a pyroelectric material of course is noncentrosymmetric, so it will have some deviation of, so let us say this is the polar vector. So which means the pyroelectric material is spontaneously polarized. Okay. Now for a pyroelectric material, when you change the direction of electric field, let us say in this case the electric field was in this direction. When you change the direction of electric field, this polar vector does not change. So which means this central atom still gets shifted into this direction. So which means direction of P does not change when you reverse the polarity of E, and this represent pyroelectric. For a ferroelectric, what will happen is, so this is, let us say, P direction and this is E direction, and when you reverse E, when you make E in this direction, the P also becomes in this direction. So direction of P reverses as E reverses. So this is another constraint which has been imposed on ferroelectric materials. So naturally, by definition, all the ferroelectric materials are pyroelectric materials. So now you can summarize these three. Piezoelectric materials are, the only constraint is that they have to belong to the category of non-centrosymmetric point groups, with the exception of 432. So there are 20 non-centrosymmetric point groups, and all the materials belonging to these point groups will be piezoelectric in nature. Pyroelectric, there is a constraint, the material has to be polar in addition to being non-centrosymmetric. So there are 10 point groups, the materials which belong to these point groups are piezoelectric in nature, and they have a unique polar axis, which means they are spontaneously polarized. And then the third category is ferroelectric material, in which not only they are non-centrosymmetric, not only they are polar, not only they have a unique axis, but this unique axis, the direction of this unique axis is reversible when you reverse the direction, when you change the direction of electric field which is applied. So naturally there is furthermore constraint on the pyroelectric, which means not all the pyroelectric materials are ferroelectric, but all the ferroelectric materials are pyroelectric. So when you now make a diagram, so let us say, so these are 20 non-centrosymmetric point groups, which means all piezo. So these are all piezo. Out of these, so this is 20, out of these 10 are pyroelectric, which are also polar in nature. Okay. And out of these you will have some, that number is not very well defined because it depends on the type of material, some which are ferroelectric, for which polarization direction can be reversed by reversing the direction of applied electric field. So, ferroelectric material is the smallest subclass out of all these 20 non-centrosymmetric polar groups, and that is why they are very limited in numbers. So, again to reiterate, all the ferroelectric materials are pyroelectric, but reverse is not true necessarily. Similarly, all the pyroelectric materials happen to be piezoelectric, but the reverse is not true as well. So, this is a sort of introduction to the crystallographic basis to differentiate ferro, piezo and pyroelectric materials from the other dielectrics that we have learnt in the previous classes. Now, what we will do is that in the next class, we will finish this lecture here. What we will do in the next class is we will take up the discussion on ferroelectric materials to begin with. We will look at the how these materials evolved and the basic characteristics of these materials, and then we will evolve a thermodynamic basis to understand these materials, because these materials also show they are also associated with certain phase transitions which are unique in nature, and then finally we will look at the applications. So, we will finish this lecture here. So, to summarize, what we learnt was that you have these nonlinear dielectric materials which have unique properties like large dielectric constants. They can also have large polarizations. They show effects like coupling of mechanical and electrical order parameters, and correlation between temperature and the polarization, and then they have these hysteresis loops, presence of non-zero polarization at zero field, and all these effects are associated with the nonlinearity in the when you plot polarization with electric field. And this class of materials are very unique in nature, and they have huge technological potential, and some of these are already used in variety of applications. Fundamentally, they belong to class of materials which are non-centrosymmetric in nature. So, out of these all the non-centrosymmetric materials except the 432 point group materials happen to be piezoelectric, which means they have this mechanical and electrical coupling. Out of these non-centrosymmetric, only polar ones are pyroelectric, which means they have a unique polar axis, and out of these 10 polar non-centrosymmetric crystal classes, point groups, you have not crystal classes, rather point groups. So, out of these 10 which are non-centrosymmetric and polar, there are some which are ferroelectric, in which this unique polar axis, the direction of polarization along that polar axis can be reversed by reversing the direction of applied field. So, we will finish this lecture here and see you next time.